Hello, people of the class. Welcome back to another installment of physical chemistry. Welcome back. It is Friday, right? Thank God it's Friday. Happy Friday, and I hope you guys have a good one so far. Let's see, some things, well, we already kind of talked about it in the last video, so I don't really need to go over it too much. But just don't forget that chapter 6 homework is due on, I think it's 5 and 6 actually, is due on Wednesday of next week, I believe. And also on Monday, we are having our meetup, our coffee hour meetup. So be there or be square. I think I sent you out the Zoom meeting invite. Yeah. Okay, let's continue with PChem. So we've gone through single component systems, and we've described their equilibria. Now we want to come back and talk a little bit about, or talk a lot about multi-component systems. And this is the point that we've been trying to get to basically the entire semester. Can we define the equilibria of a chemical system or a chemical reaction using the thermodynamic principles that we have laid out thus far? And the answer, of course, is yes. But let's work our way into it slowly. And I want to start out with something that was actually in chapter 6, but I didn't cover it in chapter 6 because I didn't think it quite made sense there. But now that we're getting into multi-component stuff, it makes sense to begin to start talking about the Gibbs phase rule. I don't know if you can hear my family in the background. Having a great morning. The Gibbs phase rule. Basically, what the Gibbs phase rule sets out to answer is how many variables must be specified in order to determine the phase at equilibrium. Okay? So how many variables must be specified in order to determine the phase at equilibrium? In this case, the variables are equal to, the known variables are equal to what's called a degree of freedom. Oops. Okay, so the variables that you have to define are equal to degrees of freedom. And I guess the phase rule more succinctly is what's the smallest number of degrees of freedom? Oh yeah, I call these DOFs, by the way. Just make it nice and short. What's the smallest number of degrees of freedom needed to describe the state of a system? Okay, this is what the Gibbs phase rule is setting out to answer. The smallest number of degrees of freedom, the smallest number of pieces of information about the system to completely describe the system in its entirety. Okay, and I know that I said that we were doing multi-component, but actually I want to go back to single component for just a little bit. Okay, let's go back to single component for just a little bit. And let's look at the two-dimensional phase diagram for water. Okay, this is the two-dimensional H2O phase diagram. We have this sublimation line here, then we have the triple point, then it goes up like that, and then it comes over this way. I guess up here we have the critical point, and we have a solid here, we have a liquid here, and we have a gas here. Okay, this is the two-dimensional phase diagram for water. If we know, okay, let's do a couple different scenarios. First scenario, if you know only H2O exists, so only H2O is present in this system, and that the phase is a solid. So we have a solid phase, we have only H2O. That means that we can have any pressure temperature. Whoa, what's going on? We can have any pressure temperature value that is within this shaded region here. Okay, we can have any pressure temperature value there. And that's because we haven't given enough degrees of freedom. Okay, so we can't perfectly describe the state of the system because we only know that it's a solid. All right, let's do a second example. All right. If you are told that you have, okay, well, hold on. Sorry, I'm skipping ahead a little bit. Okay, so if you're told that the phase is solid here, you can't figure everything else out. So you must be told the pressure, the temperature, and the phase if you want to completely define the system. Okay, so this is 3 degrees of freedom, right? Now, what if I told you that you have both a solid and a liquid phase? Okay, so you have both solid and liquid phases. What does this mean? If I look at this graph, where on this graph can you possibly have both a solid and a liquid at equilibrium? If you said this line here, you are 100% correct. Okay? Along that line, you can have both a solid and a liquid in equilibrium with each other. If that's confusing to you, please make sure to go back and double check chapter 6, because that's basically what we talked about the entirety of the chapter. Okay, so if we're on this line, that means that we have 2 phases, right? So we have both a solid and a liquid. And if you can see this, you only have to now define either the pressure or the temperature. And since you're on this line somewhere, that means that if you just make one of those variables match up correctly, then you've completely defined the system. Okay, so that means that you need either P or T. You don't need them both, right? So now we have 2 degrees of freedom, right? So 2 degrees of freedom. This is we have decreased the number of degrees of freedom, and we have decreased the number of degrees of freedom with the phase number increasing. Okay, so since the number of phases present has increased, the degrees of freedom has decreased. That means that there is a relationship between the degrees of freedom and the number of phases. Okay. There is a relationship here between these two. And this relationship is a relationship that Gibbs defined or exploited in a way. Okay? Good old Willard. I might name, if I ever have a boy, I have 3 girls, you guys know. But if I ever have a boy, maybe I'll name him Willard. What a great name. Willard. Mr. Gibbs. Yeah, then I'll call him Mr. Gibbs all the time. You guys hear that? That's my child, the youngest. She's running around out there. Tried to annoy the 2.5-year-old in the background. Yeah, good old Willard. He came up with this basically a relationship where he defined the relationship between the degrees of freedom and the number of phases. And he found through process of elimination and empiricism that the degrees of freedom for a system is equal to 3 minus the number of phases. Okay, that's P is equal to the number of phases. This is only true for one component systems. Okay, so this relationship is only true for one component systems, but it begins to answer a very important question here, which is that the degrees of freedom, or the number of pieces of information you need to define a system, is dependent on the number of phases. However, it turns out that it's also dependent on the number of components. So when you have a multi-component system, which is what we're interested in defining now, okay, so for multi-component systems, more information is obviously necessary. Okay, we can't figure out the number of degrees of freedom by simply using this equation up here. We have to come up with a different relationship. Okay, so before we do this, I want to point out some assumptions and observations and simplifications that we can come up with. So assumptions, observations, oh, somebody's hurt, and simplifications. Okay, and this just makes it a little bit easier to actually define the degrees of freedom of a system, because if you think about it, if you start adding more and more stuff in, it becomes more and more complicated, right? This makes sense. So at some point, we need to make some assumptions and observations and simplifications, just because if we don't, it would become too massive of a problem. Okay, the first assumption is that the system is at equilibrium. Okay, system is at equilibrium. And because of this, right? Because of this, all the components within the system experience the same temperature. And actually the same temperature and total pressure. Okay, they all experience the same temperature and total pressure. That means that T sys is equal to T component 1 is equal to T component 2 is equal to T component 3 ... Okay, so all of the components within the system all experience the same temperature, and this makes sense if you think about it. And all of the components of the system also experience the same total pressure. So the pressure of component 1 is equal to the pressure that component 2 experiences, is equal to the pressure that component 3 experiences, etc., etc., etc. Now this here, be careful here, because this does not mean that the partial pressures of each of the components are the same. This is not what I'm saying here. I'm saying that the total pressure that is experienced by the entirety of the system, by all of the pieces within the system, is the same. Okay, not the partial pressures. The total pressure is the same. Okay, so we can also make some statements about all of the phases within the system. So all of the phases experience also the same pressure and temperature. Okay, so not only the components, but all of the phases are also experiencing the same pressure and temperature. So we can say that T sys is equal to temperature of phase 1 is equal to temperature of phase 2 is equal to ... And then the pressure of the system is equal to the pressure of phase 1 is equal to the pressure of phase 2 is equal to ... Okay? In addition to this, we're also going to assume that the system is isochoric, meaning that the volume is constant. Okay? And we're also going to assume that we know the total number of moles. Okay? So these are basically all of our degrees of freedom that we have to work with. The question now is, how many degrees of freedom are needed to describe the state? To completely describe the state. Well, if we look at this list of stuff and we really think about it for a long time, we could come up with an answer, but thankfully, good old Willard has already done it for us with the complete phase rule, which looks like this. We have degrees of freedom is equal to F. F is just another way of saying degrees of freedom. F is equal to C minus P plus 2. Okay, so C is the number of components, P is the number of phases, and 2 is 2. Okay, so now we have a description for the number of degrees of freedom that we should describe for a system given a multi-component system, or given a system that has more than one component. Okay, and this is the complete Gibbs phase rule. Okay, complete Gibbs phase rule. For example, let's do some examples here. Well, actually, you know what? These two examples, 7.1 and 7.2. As part of your lecture today, I want you to go through and walk yourself through those two examples. They, within the book, they are super useful. And they're useful at illustrating exactly what this equation here is talking about. Okay, example 7.1 and 7.2 are super useful. Okay, now it's kind of useful to start talking about specific multi-component systems. Okay, because specific multi-component systems start behaving in similar ways. Whoa, that was such a bad specific. Okay, specific multi-component systems. The first one we're going to talk about is two-component liquid-liquid systems. That means that both of these things are in the liquid phase and they are mixed together into some system. One thing that's important here is that these two components are not interacting chemically. Okay, they're not interacting chemically within this this specific multi-component system. Okay, let's consider a binary solution. Let's consider a binary solution that has two liquid components that are not interacting chemically. We can use the good old Willard's phase rule. So F is equal to C minus P plus 2 to determine the number of degrees of freedom we have to define in order to completely define the state of this system. Okay, so we have C. C is the number of components. We have two components. This is a binary system, so we can mark that in as 2. Minus the number of phases. This is all of the phases are liquid here. So we only have one phase present. So that's 1 plus 2, and this ends up being 3. We have to define 3 degrees of freedom. 3 degrees of freedom in order to specify or define the system in its entirety. Okay, so for example, what can we specify? We can specify what makes sense to specify. We can specify temperature, pressure, and mole fraction of one component. This is 3. That means that we've completely defined the system with these 3 pieces. And we know that we've completely defined the system because of Gibbs phase rule. Okay? By the way, we can find the second component. So mole fraction of component 2 is equal to 1 minus mole fraction of component 1. Right? Because this is a binary system. So we can necessarily figure out the fraction of the other by subtracting component 1 from 1. Okay, that's just how mole fractions work, which means that we have accurately and completely specified the system using only 3 degrees of freedom. And once we know all of these things, we can say whatever we want about the system. We can define the system in its entirety. Okay? So I will stop there for today, and we will continue with this specific multi-component system on Monday. Don't forget, we have this meetup on Monday. We're going to be doing that during the normal time, but I'll still be posting a video on Monday as well, talking about multi-component rules or multi-component systems. Please be sure to go through and do the examples 7.1 and 7.2. And I will see you next time.